Welcome back, grade 11s from the break. So we have just looked at the patterns that the fields, the electric field makes around a charged object. We've also had a look at the direction. So remember, it has a magnitude, but it also has direction. So the direction needs to be put into our patterns, the drawings that we make with the lines. Now we're going to look at field strength. So we've looked at how to represent the field. Now what about the strength of the field? So on my board here, I have a picture of a field around a negatively charged particle or object. Now, this is the formula that we use to find field strength, so electric field strength. What is it really? This Q, this baby Q, it's a baby Q, a little Q, that is representing the test or positive point charge. Now, I'm hoping that you're picking up a pattern here. We always use a a teeny positive point charge as a test. So if we place this little test into the field, what is the force going to be on this little test charge? So that is going to give us the electric field strength or the electrostatic field strength. So here we've got the formula force, so F stands for force. So it is the force per positive point charge. And it's really little, so it almost has like a negligible effect on the original field. So there we go, there's our formula. E stands for the electrostatic field strength. So E stands for strength. And how do we measure that? We measure that by looking at the force that is exerted on a positive point charge or per positive point charge. So that is how we're going to look at the field strength. Now, we're looking at this little point charge and we're thinking, well, it's possibly how are we going to work out this force that is exerted on this little point charge. And it brings to mind Coulomb's law. Now, you've probably seen Coulomb's law before. So Coulomb's law. And Coulomb's law is about the force that is between two charged objects. So it's the attraction between two charged objects divided by the square of the distance between them. Okay, so if we put this little positive point charge, this test charge, into the field, you can see I've got a different field now. Can you see that? So now it's in a field created by a positive charge, and of course the direction is away. You can see there the direction is away. So this point charge would be pushed away, right? It would be pushed away like that. In the other one, I was going to go back. In the other one, it would be attracted. So it would go towards that negative charge. Now we're dealing with the second kind of field, which is where we've got a field around a positive charge, and that's going to repel the positive point charge. So how does Coulomb's law fit in here? Well, we've got two charges here. We've got this little one here, over here, and we've got the one that has the field around it. So this one over here. So there must be a force between these two charges. We're going to use Coulomb's law to figure that out. So this would be Q1, okay, would possibly be the original charge, and here's Q2, and so we could place in this Q here. Okay, so that's what we're talking about. We're talking about the force between the original, the big charge, and this teeny weeny little point charge. If we substitute Coulomb's law into this equation, this is what we're going to end up with. We're going to end up with E equals, what is force? Well, force is Q1 Q divided by R squared, the distance between them, there's R, okay, divided by Q. Okay, you see that? So this part here is Coulomb's law. That's the force. Okay, there we go. That's the force. We're trying to find the force. There we go, the force. This Q over here is the one that we're saying per unit point charge. So we can solve for this equation. We can use mathematics to move it around a little bit, and we end up with, I'm going to move on to this side, EQ equals KQQ over R squared. We can then remove those two, and we end up with E. I'm moving along this way, I'm running out of space. E is equal to KQ over R squared. Right, so here I have it all written out neatly, better than the previous slide. Okay, so what's this telling us? Well, remember E stands for the electrostatic field strength. What is it related to, or what is the relationship for this electrostatic field strength? It is related to the charge that has the field around it. So if I draw this charge again, so here's the charge, I'm just doing a positive charge. So let's say we've got this positive charge, okay, and we pop into it this little positive point charge. The strength at that point, the strength at this point here, is going to hinge on, it's going to rely on the magnitude of this charge. So there it is. The magnitude of the charge is responsible for the field. So if it is a small charge, a small value, then the field strength is not going to be that great. If it is a big value, if that charge has a big value, then obviously the field strength is going to be much bigger. It is also determined, the field strength is also determined on the distance where the point charge is sitting to the main charge that is giving us the field. So if this is a small distance, then obviously the field strength is going to be bigger. If it is a big difference, so let's say the point charge is right over here, can you see that that distance is far greater? And so the electric field strength is going to rely on the distance from the original charge to the position of the point charge. Okay, that is a really good formula for us to use. Obviously, K from Coulomb's law is Coulomb's constant, which is 9 times 10 to the 9. So you'll get that from your data sheet. Let's dive into a problem, because that's really testing our theory. We've done a lot of theory now. Let's see if we can answer these questions. So this is the problem. Two identical, it's very important, two identical point charges, X and Y. So there they are there. So there's X, you can see them over there, and there is Y. Okay, they are identical, are placed 2 millimeters apart. Point P is over there, point P is 3 millimeters to the right of charge Y. So you can see to the right, okay, there's to the right. And they've given us a really nice picture here. The net electric field at point P is 5,44 times 10 to the 6 Newton per Coulomb. And it is to the left. So remember, this has to have a direction. It's a vector quantity. So it is to the left. So that's going to tell us something about the charges. What are they asking us first? The first thing is define the term electric field at a point. So that is a definition that we need to know. What is the term electric field? Well, it is the force experienced per unit positive charge, isn't it? If we've got this formula that we started off with right in the beginning, force divided by little q, from there we can write the definition. So it is the electrostatic force, and I'm just going to write this really quickly so we can get through the other stuff, experienced per unit positive charge. Okay, I hope you can read my writing. But that's learning work, right? So you can do that. You've got this. The next one is, are the charges negative or positive? And I've rewritten this here because this is important. This force that is being experienced is by P is in that direction. It is left. So something is drawing this. This force is in that direction. It's in that direction. So what do you think this is going to be? Well, because it is to the left, because this force is being, this electric field is being experienced to the left, it means that these charges, the x and the y, have to be negative. Okay, negative. If they were positive charges, then the field strength would be experienced in the other direction. It would be experienced in the right direction. Next question. Draw the resultant electric field pattern for the charges x and y. So we now know that they're identical. They've told us they're identical. That's really, really important. So we know that x is going to be negative, and we know that y is going to be negative as well because they are identical. So what's going to happen? There's going to be repulsion, and so our field lines are going to look like this in the middle, and they're going to be warped to there and warped again because they're being pushed away. They're pushing each other away. We need to keep in mind that they need to not cross, that they need to be 90 degrees to the surface. What about direction? Negative. If we put a positive point charge into this field, then it is going to be pushed away. And so that is the direction of the electric field. Okay, I'm going to move on because I'm running out of time here. Calculate the magnitude of charge x. Oh my goodness, isn't that a whopping question? But loads of fun. So let's get into how we are going to solve this problem. We do have a formula. E equals kq over r squared. Okay, we've just seen to that. What do we know? Well, we do know distance, don't we? We know the distance between x and y, so we know that distance. We also know the distance from x to p. How do we know that? Well, we know that it's 2 millimeters plus 3 millimeters. Why am I concerned about P? Because I do know what the electric field strength is. They've given it to us. The electric field strength, let me go back because I can't remember it offhand, was 5,44 times 10 to the 6. So we do know this. They've given it to us. So the electric field strength E, the electric field strength, is 5,44 times 10 to the 6 newtons per coulomb. So we know this. So if we look at this situation, we can see that charge Y is going to influence P. We also know that charge X is going to influence a P, or that point at P. So both of them are going to have an effect at that point where P is. So we can write here that E net is equal to the electric field charge, electric field strength of X on P plus the electric field strength of Y on P. And they both will both influence that position at P. So let's write that in. It's going to be K, Q, and in this case it would be X, right, over the distance between X and P. And so that's going to be 5 millimeters. But now we can't work in millimeters, we need to work in meters. So we need to change that into meters. So it's going to be 5 times 10 to the minus 3, and we need to square it, plus K, Q. Now, X and Y are the same, aren't they? They are the same because they are identical. The distance between Y and this point P is 3, so it's going to be 3 times 10 to the minus 3, and we square it. K is going to have a value from our data sheet of 9 times 10 to the power of 9. Once we have worked all that out, I've forgotten to put E in, so E net is going to be 5,44 times 10 to the 6. Right, once we've worked all that out and we've substituted in K, we come up with an equation that looks like this, or working out that looks like this. I'm going to write on the right-hand side, I've run out of space, and so we end up with Q, because remember Q and Q are the same, QX and QY are the same, they are the same. So that means that they are similar terms, they're same terms, so we can add those values together. We get 5,44 times 10 to the minus 6. Sorry, not to the minus 6, to the plus 6. Let's turn that into a plus. Divided by 1,36 times 10 to the 15. And our answer then is 4 times 10 to the minus 9 coulomb. That is Q. In other words, that is the value of X. And we know that its charge is negative. So X has got a charge of negative 4 times 10 to the minus 9 coulomb. Right, grade 11s, I hope that has helped you with how to use your theory to answer these questions. We will see you next time.